So today we'll be discussing about quantum numbers. Okay, so as we all know that electrons are situated in an atom in a particular address, and for that address we use these quantum numbers. Alright, so quantum number are of 4 sets. So you have 4 set of quantum numbers and they constitute the address of an electron. We could know where the electron is situated by just knowing about these quantum numbers. So first quantum number is principal quantum number. Principal quantum number, which is actually the shell number. Okay, it is denoted by the letter N. It essentially tells about the shell number, the energy level, or you could say the orbit number. As you know, there are many orbits around the nucleus, or period number. In a periodic table, you have periods and groups. So it is period number or energy state at which the electron is situated. Okay, so the values can be 1, 2, 3, etc. The natural numbers, and they are well defined and discrete values. Now completed this shell number. Now second level is azimuthal quantum number, which is denoted by small letter L. It is essentially the number of subshells, which are in an orbit. So you have, if you are considering one, so shell will have a set of numbers, subshells. So that number is denoted by this L. Now value of L over here is N. So value of L can go from 0 to N minus 1. So if you know the value of N, you can easily find out value of L. This is the equation to find out N. Also, an important thing to know is that L can never be equal to N. For example, if N is equal to 0, so L will also be equal to 0 because it is going from 0 to N minus 1. So here it is 0 itself. Alright, and it will denote the S subshell. The S subshell. L equals to 0 means S subshell. N is equal to 1. Then what happens? L is 0, 1, and it denotes the, and if N is equal to 0, then L can be 0, 1 and 2, and it denotes that it is the D subshell, and so on. Next, you have third quantum number, which is magnetic quantum, which is denoted by small letter m. This is actually the number of possible orientations which are possible with respect to the nucleus of electron in a subshell. A subshell has a number of possible orientations that is denoted by this quantum number. Okay, m have values from -L minus L is the azimuthal quantum number to plus L. So if you know L, you can find out M. For example, if L is equal to 0, if L equals to 0, is equal to 0. Okay. And as you know, if L equal to 0, it will be S subshell and the shape is spherical. The S subshell is spherical. So you know it can only be have one orientation. It's a sphere and you can't expect any other orientation. That's why M equals 0. Okay. Now next you have L is 1. So will be equal to minus 1, 0. Because you are going from minus L to plus L, so you get 3 magnetic numbers. And this is a P subshell, and you know a P subshell is a dumbbell shape. Okay, so that's orbital, and if here you have P orbital, which is a dumbbell shape. Okay, so the dumbbell, as you can see, it is something like this. Now this can have 3 orientations, which is X, P, Y and P, Z. These are the 3 orientations that you can have along the respective axis X, Y and okay, X, Y and Z axis. Okay, so this is essentially the magnetic quantum number of P7. They are having same energy. Also, the thing to note here is Pz is the one which is having M equals to 0. Pz, and the both of them can have minus 1 or plus 1 respectively, or in any zero, but the note Pz is having magnetic quantum number as 0. Okay, and this point where the electron is not expected to be seen, this is known as Orion, and the lobes. I hope it's clear. Next, if you have L equals 2, then M can have values from minus 2, minus 1, 0, 1 and 2. And this denotes the D subshell, which is a double dumbbell shape. Double dumbbell. So how would it look like? It will look like this. Here we have 2 dumbbell-like shapes attached together, and we have 4 lobes. And here, you know, you have 5, so you have dx square minus y square. These are the orientations, right? So we have dxy, dyz, dxz and dz square. Alright, and the point to note here is the dz square is the one which is having m equals 0. All the others can have any other values, but dz square will have m equals 0. That is because we take one axis as a reference, and the orientation which comes along that axis we take m equals 0. And another note here is the penetration power. The penetration power order of these orbitals, the SPDF, is S will be having the most, then P, D and F. S will be having the most penetration power, and it will be more closer to P's than other orbitals. I hope this is clear. Next is you have L equals 3, then M will be minus 3, minus 2, minus 1, 0, 1 and 2. Here you have 7 orientations possible, and here you know it will be the F subshell, and this will be having a triple dumbbell shape. Okay, and it's complex, and the note here is you will have ZQ, which will be having the n equals 0, and all the other names are fx cube, fy cube, fxy square, fx square minus y square. These are all the possibilities, and f z to y square minus x square, f y square minus z square, and the last one is fz cube. So these are the possibilities that you have. So the thing to note here is the which ones are the s orbital, the pz orbital, the dz square, and the fz cube. These are the ones which have m equals 0 value. And the shape of f orbital, you can just draw 3 orbitals. It will be like a flower actually, and we'll have a node also. So this is the f subshells. Now the last one is you have spin quantum number. This is actually based upon the direction of rotation. Alright, the electron is revolving clockwise or anti-clockwise. So it is denoted by S or MS, you could say, and it will have only 2 values, which is it can be either plus half or it can be either minus half. So if it is plus half, that means the electron, you can see this is an orbital, and 2 electrons can reside here. So you will have 1 electron and you will have second electron, and both of them will never ever have the same direction of spin. So if one has plus half, so the other will be always minus half. So if this plus half, that means is rotating clockwise, and this was anti-clockwise. This is the spin quantum number, and it's simple. So these were the quantum numbers which help to give an electron an address and to find out where the electron is situated. Thank you.